we have defined entropy production, and we've looked at entropy production for a closed system undergoing a process, say 1 to 2. Now let's look at entropy production rate for an open system. So remember, what's the difference between an open system and a closed system? The open system, of course, has got a closed mass. Mass is fixed. An open system, of course, you've got mass flowing in, mass flowing out. And by and large, for most of your engineering problems, your homework problems, your quiz and test problems, most of them involve steady state, steady flow situation. In other words, things are operating steadily in time. What's going on at breakfast time is the same as what's going on at lunchtime. So let's look a little bit back. Let's do a crash course to be sure everybody is up to speed on the fundamentals. So let's remember that entropy is a property. Okay. And so there's a property called entropy. It's a measure of disorder. So the higher the numerical value for entropy, the more disordered the substance is. Let's see. A common analysis for practicing engineers is to deal with open systems. And in fact, in most of your problems are going to involve open systems operating at a steady rate. Remember, it's all about the dots. When you have an open system engineering situation, you've got mass flow in, mass flow out. For one inlet and one outlet, those mass flows are identical. Remember that your sketch is going to have dots over top of M. It's not just mass, it's mass flow rate, M dot. Similarly, heat is flowing into the system at a certain rate, Q dot, and power is being generated by the open system, so it's W dot. And then remember in the back of your mind, the textbook uses an awful lot of these little q's and little w's, and remember that that little q is going to be Q dot divided by M dot, and little w is W dot divided by M dot. It's rate over rate, and that's the way you get little q and little w in terms of units of kilojoules per kilogram. Now, let me see if I can chase you back to your textbook a little bit and give you a screenshot of section 6.9, because what I'd like to do in this video is really talk about open systems that are operating at steady state, steady flow situations. So let's look at equation 634 and see if we can simplify it. And of course we can. So there's equation 634. Remember, I talked a little bit about how I had a hard time understanding about this entropy production business until the light bulb finally went on and said, well, I'm gonna solve these textbooks equations. I'm gonna make sigma equal something. And that's what we're going to do here. Let's look at equation 634. And the leftmost term says the rate of entropy change within the open system, ds dt of the control volume. That's what that variable is all about. Well, we've got steady state, steady flow. So the rate of change of anything is zero. It can be entropy, internal energy, anything. So the left-hand side of this equation 634 becomes zero for steady state, steady flow. So zero equals. The next three terms are labeled rates of entropy transfer. Now that kind of makes a lot of sense to me. The first term is going to be some type of heat transfer term that we'll talk about in a second. Here is the middle one is m dot n little s n. So do you see how you're transferring entropy into the open system, but by nature of mass flowing in at a certain entropy level, minus some outlet rate of entropy transfer, m dot leaving times s little s leaving. So those are three rates of entropy transfer term plus the rate of entropy production, sigma dot. So here we go, sigma dot, and then let's jump down to my rearranging of equation 634. Sigma dot, so that's going to be called the entropy production rate. I'm going to put a dot over top of sigma. It's a rate of entropy production. It's going to be kilowatts per degree K. That's what that's going to be, kilowatts per degree K. Okay. equals the entropy transfer rate terms. Now, so as I rearrange these, do you see that this term is going to have a minus sign tied to it, a pesky minus sign tied to it? Okay, we're going to flip to the other side. So we've got the sum of the m dot leaving, little s leaving, and then minus the sum of the m dots coming in times little s in. Okay, so this is a good working starting point when you have an open system, steady state, steady flow. This is the governing equation that I recommend you use rather than starting with equation 634. Just remember, steady state, steady flow, multiple inlets, multiple outlets, and there's going to be possibly some number of heat transfer rates coming into the open system control surface. And here's a pesky minus sign that you got to remember to deal with. Okay, now let's simplify our situation. Okay, so anyway, we're not going to simplify our situation. We're going to make some observations about, is something possible or impossible? That frequently asked questions. So I see that I've got my sketch of one inlet and one outlet, but in my fundamental equation here for entropy production rate, I've got multiple inlets, multiple outlets, and the possibility of multiple heat transfer rates in. Okay, so that's a general statement. That's good. My sketch is only one inlet, one outlet. But now, here's the big reveal for this slide, right? We can make some statements about the second law of thermodynamics now that we're good at calculating entropy production rates for open system processes. But it's just a process, 1 to 2, okay? So we can say that when sigma dot is greater than 0, the process is possible and it's irreversible. There's something going on within the process that's irreversible. Okay, when sigma dot exactly equals 0, not only is the open system possible, it is a reversible open system. And when sigma dot is less than 0, the proposed process is just flat impossible. Whatever the salesperson or inventor is trying to claim, that would be an impossible claim or proposal. So this is a way to sort of put it all together and relate entropy production rate, which will be some numerical value, kilowatts per degree K, and relate that to the second law of thermodynamics, saying what's possible and reversible, and what is just flat impossible. It's so important that what I wanted to do is make it reduce the word count. I wanted to create another slide that reduces the word count. Okay. Commonly asked question, is a proposed steady state, steady flow open system process possible or is it impossible? All right, so just a rehash, just to really make the point. Let's go to the right. If sigma dot, that's the rate of entropy production, if it's less than 0, the proposal is impossible. What if it's greater than or equal to 0? You've got two situations. If sigma dot exactly equals 0, you have shown that the proposed process is both possible and it's reversible. If it's numerically greater than 0, it is possible and it's an irreversible process. The process has got some kind of irreversibility in it. We're going to be able to quantify that here shortly in another video. Let me see what I've got here. Now we're going to look at getting towards an example of identifying the entropy production rate numerically. Let's simplify our little example down to one inlet and one outlet. So here's our basic governing equation with all these sums in it. Let's just look at a situation where we've got one inlet and one outlet. So therefore, m dot in equals m dot out equals m dot. Okay, so here's our sketch. We've got any kind of open system. I've shown it as some trapezoid, but it can be any open, any kind of cloud. Anything. All right, open system. All right, I've got one instance of heat transfer rate Q dot, and it's going in. I'm showing it as in. Okay, and heat is being transferred into the control surface from T of the surroundings. I'm calling it T, S-U-R-R, T of the surroundings. How will we compute sigma dot? For this example, how do we come up with a value, a numerical value for sigma dot? Okay. Well, here it is. We're going to look at, okay, we've got sigma dot equals, here's our pesky minus sign. There's only one heat transfer in, so we've got Q dot N divided by the temperature at which it's being transferred from the surroundings, T of the surroundings. So we've got minus quantity Q dot over T of the surroundings. That's the first entropy transfer term. And then the next two, they simplify. Here's exit, here's inlet. So we've got one M dot. So we got M dot times, based on our sketch, S2, that's what's going out, minus S1, what's coming in. All right, so if you're thinking about formula sheet or special formulas you're going to write down, you got to be careful that if you're going to write this down, you got to remember it needs to include a sketch. So one occurrence of heat transfer in from T of the surroundings might be hot, okay? The pesky minus sign, don't forget the pesky minus sign, plus M dot leaving, S entering. Let's do a numerical problem real quick to illustrate a numerical evaluation. So, and it says, in ideal gas, the ideal gas air is flowing into a fully insulated turbine. Fully insulated turbine. Oh, yeah, right. Okay. At a rate of 3 kilograms per second, that's M dot, with a pressure of 1 megapascal and a temperature of 400 degrees K. The turbine exit pressure is 100 kPa. Wow, a lot of information. During this process, the specific entropy of the air, S2 minus S1, increases by 0.15 kilojoules per kilogram degree K. So little S2 minus little S1 equals plus 0.15 kilojoules per kilogram degree K. What's our assignment? Draw an equipment sketch of the process. That's a no-brainer. Next, draw a TS diagram depicting the process. That's a no-brainer. You don't need to be told to do that. And then finally, determine the rate of entropy production for this process. So that's what we got to figure out. What's sigma dot? This could be a classic quiz or test problem. It's going to be pretty easy. All right, here is our sketch. Our sketch, we've got an insulated turbine. I'm showing it as Q dot N is 0. Inlet state 1, outlet state 2. Here's my TS diagram. Let's see. It says I've got no heat transfer and I'm increasing my entropy. And so now I'm going to have to go do through the numerics. So I don't know this exactly, but I do know that S2 minus S1 is a positive number. So at least I know that state 1 is going to be at a high pressure, given. State 2 is going to be at a lower pressure, given. Okay, here's state 2. And I know that state 2 is going to be to the right of state 1, because given in the problem, S2 minus S1 is a positive number. All right, so there's my sketches. Okay, the next thing, let's do the numerics. Sigma dot is equal to pesky minus sign, minus Q dot over T. Well, what is that? What's that whole term? It's 0. Okay, great. M dot given 3 kilograms per second, S2 minus S1 given. Okay, and so sigma dot is plus 0.45 kilowatts per degree K. I'm going to put a big green check mark because that process that was described in the problem statement is possible and irreversible. Okay, and so now that's why I have a dashed line on my sketch. I jumped the gun a little bit on my sketch. So the dashed line means the process is irreversible. All right, pretty good example problem to prepare you for a quiz or a test. Example problem number 2. An engineer proposes an industrial compressor process, a compression process, that involves heat rejection from the casing of the compressor. Okay, so Q dot N is going to be less than 0. Your job is to determine if the proposed process is possible or impossible. And if possible, determine if the proposed compressor operates in a reversible or irreversible manner. Let's see if I've got any numbers associated with that. Okay. Gee, so I've got, uh, so far, I don't see any numbers. So I've got visualization of a proposed air compressor. I've got heat rejected to the surroundings, so I'm showing in my sketch Q dot N is less than zero, even though I'm showing an arrow. Well, I'm showing an arrow out. Oh, shame on me. So Q dot N is less than zero. So I'm depicting heat rejected to the surroundings. Room air coming in, compressed air to the industrial process coming out. Okay. Okay. Now I've got some numbers. Woo! Okay, so here's the proposal with numbers. The ideal gas air flow rate is 2 kilograms per second. M dot's given. Inlet conditions, a certain temperature and pressure. Outlet pressure higher than the inlet. Heat is rejected from the compressor at a rate of 40 kilowatts to a heat sink to the surroundings at 300 K. Okay, so that's going to be important. Q dot N is negative 40 kilowatts. Q dot N, negative 40. Okay. Oh, look, here's something given information. During the process, the specific entropy of that air decreases by 0.02 kilojoules per kilogram degree K. So that's going to be S2 minus S1. All right. What's our assignment? Well, draw an equipment sketch, no brainer. Draw a TS diagram, no brainer. This is going to be easy because we're given some easy input data. Determine the rate of entropy production for the process. Okay. And in the problem, it said the engineer was simply proposing this situation where we're rejecting heat from the casing of the compressor. So is it possible or impossible? We've got to determine sigma dot. And if it's possible, is it reversible or irreversible? You get the drill. Okay. Thank goodness we've got some numbers. Now we can start putting pencil to paper. Okay, here our sketch. We've shown a compressor. Okay. Now, on my hand-drawn sketch here, I'm showing Q dot N is minus 40 kilowatts. Important, right? I am showing the surroundings temperature from which the heat, to where the heat is being rejected, 300 K. M dot, showing steady state, steady flow. I've shown an M dot given. I've got a state 1 and a state 2, clearly showing that on my sketch. Okay. Let's see, TS diagram. I was given in the problem that S2 is less than S1. In other words, the specific entropy decreases. Okay. And so I'm showing state 1 at a low pressure, and I'm showing state 2 at a higher pressure and a lower entropy value. This is the way you draw your sketch. S2 is less than S1 because of the given information in the problem. Now let's do the numerics. We've got heat transfer. All right. So I didn't exactly, well, this is going to be good enough for my governing equation, isn't it? Sigma dot, steady state, steady flow equal, pesky minus sign, minus Q dot N over T plus M dot given times quantity S2 minus S1 given. So let's go through the numerics. Minus, here's my pesky minus sign, brackets, Q dot N is negative 40 kilowatts divided by the temperature at which the heat's being transferred, 300 degrees K. Okay, it's my first term. Next term, M dot, 2 kilograms per second. Entropy change, given that it's a negative number, negative 0.02 kilojoules per kilogram degree K. So I've got some intermediate calculator results. I've got plus 0.133 kilowatts per degree K minus, oh, I can do that in my head, 2 times 0.02 minus 0.04 kilowatts per degree K. So now I'll do the arithmetic to get sigma dot is plus 0.0933 kilowatts per degree K. I'll put a big green check mark on it. And because it's greater than zero, that means that this engineer's proposed process is possible and it's irreversible, thus my dashed line. Okay, so there's my question mark. It's possible and it's irreversible. So I need to show a dashed line on my TS diagram. And if I were going to turn this in for credit, here's my summary. Let's see, there's the statement of the first law. I'll put my picture over top of that. Here's my TS diagram. So I am showing my dashed line, showing it's possible and irreversible. I'm saying numerically what is the rate of entropy production, 0.0933 kilowatts per degree K. And I'm clearly writing out that the proposed process the engineer proposes is both possible and it's irreversible. Okay, pretty decent problem. Now it says example problem 4, but I only remember doing 2 problems. Oh, shame on me. This must be example problem number 3, I guess. Um, no, maybe we did. Yeah. Example problem number 4. Ideal gas. The ideal gas air expands in a reversible adiabatic open system. Sounds like a turbine. At a rate of 5 kilograms per second. That's m dot. The inlet pressure and temperature are 1 megapascal and 500 degrees K. And it says the outlet pressure is 100 kPa. The assignment is determine the rate of entropy production for this process. Okay, let's think. Okay, here we go. It's a turbine. Okay, it's an air turbine. It's expanding from 1 megapascal to 100 kilopascals. In the description of the words, it says it's a reversible adiabatic open system, steady state, steady flow. Okay. Rate of entropy production. All right. So let's go. Is this going to take us a long, if this is a quiz question or a test question, is it going to take us a long time or can we go pretty fast through this? Well, I think you're going to see, if you think about this a little bit, you're going to see that this is a trick question because I went and took a screenshot of the problem statement and it said, a reversible adiabatic process. What does that mean? It means isentropic, doesn't it? Reversible adiabatic, isentropic. So let's go through our fundamental of the description of sigma dot, the entropy production rate. Well, it's equal, sigma dot equals minus, pesky minus sign, Q dot N over T of the surroundings. Wow, it's adiabatic, that's 0, plus M dot times delta S. It's isentropic. That means that little s2 exactly equals little s1. So for this open system, sigma dot is 0. That means that this particular process is, not only is it possible, it is reversible. Possible and reversible. In fact, in other words, it's reversible and adiabatic. No computations needed. This would be an extremely fast quiz or test question. So it would be shame on you if you ended up spending lots and lots of time calculating things for this problem. Okay, we've covered pretty clearly entropy production rate for an open system undergoing a steady process. So what features characterize entropy production rate for any steady state, steady flow open system? You got to look for heat transfer. You got to know the temperature at which the heat is being transferred into or out of. And you've got m dot times entropy changes. So what features characterize entropy production rate for an adiabatic steady state, steady flow system process? If it's adiabatic, you don't have to worry about the heat transfer term, do you? Nice. Okay. What if you have an adiabatic and reversible process? What would the entropy production rate be there? We just showed it would be 0. So that's like a trick question. I hope those example problems help you get through quizzes and test problems so that you can perform well in your class, get a good grade in your class. But also, I hope that, so I got to tell you that this open system analysis of steady state systems is a very common situation for when you're practicing engineering. And so this has a lot of applications. Entropy production rate sigma dot has a lot of practical applications when you're out there in the working world evaluating whether proposed ideas, proposed processes are possible or impossible. Really valuable to you.